Yeah, here's about it. Okay. Hi everyone, welcome back. Mostly familiar faces. If anyone is new, we are nPlan and we organize the presentations for Machine Learning Paper Club. We do this every Thursday for lunchtime. Lunch is provided by Google Campus. And for the presentations, today we have Naman, and he will present the next paper in the series of uncertainty, measuring uncertainty in ML models. I'll give Naman speech.
Is there support in the video?
The what? Oh yeah, let's check.
Just check that.
Sorry.
There you go. Then?
Oh, you're in the video. Yeah, go ahead.
All right. So the paper is called Selective Classification for Deep Neural Networks. So if you've been here for the past couple of weeks, you'll realize we had a theme of uncertainty. So previously, the papers have been more focused around, I'm giving you this classification result with this uncertainty, whereas the slight difference in this paper would be you're actually going to abstain from a prediction if you are not sure. That's kind of the premise. So, abstract. So the introduction is kind of talking about the concept of like self-awareness and knowing what you don't know. And so we're going to be talking about selective prediction, also known as a reject option. So the option to reject an input and abstain from classifying it. So if you want to, there's a bit of a motivation in the second paragraph, which can say like, why won't this be useful? I think they give a nice example of like for example, a self-driving car. So in the case of a self-driving car, if it can make, so suppose there's a classification algorithm somewhere in there and it's not sure about what to do, you shouldn't just go for the most probable thing, or the thing it thinks is most likely. You should just abstain. And I guess in the case of most electric cars, you just detach and give the driver full control again. So that's quite a nice use case for this. So current works on neural networks involve a cost-based rejection model. So you would weight the cost of abstaining and misclassifying. So you'd weight the cost of abstaining, alongside your normal loss function, and you'd optimize accordingly. However, I think the problem with this is that you will these weightings are they're hard to make a reasonable. They're hard to reason about what they should be. So I think they give an example of, imagine trying to set up a rejection/misclassification cost for disengaging an autopilot driving system. So it's quite hard to know how much should we value the cost of abstaining. And another thing I think is quite just noteworthy here is at the moment we're using a softmax response. So that's currently the way a lot of the work is based around. So this is kind of covered, but I think if you're all familiar with softmax outputs for classes A, B, and C, you will have these would be your softmax outputs, and what you would do is you would define a threshold theta, and you will not make any prediction unless the highest probability, well I don't say probability, the highest output in your softmax vector is above this threshold. So in the case of, in this example, with the same theta, you would abstain from making a classification. So that's quite simple. Okay, and now they go on to talk a bit about ensemble techniques. So this was covered in Paper Club 2 weeks ago, I believe. But I think just to give a summary on it, you can, what it is it involves training the same model, so it would be the same architecture, and using many of their outputs to determine the certainty of a prediction. So, I mean, the most the most obvious way to think about it is if most of the classifiers in your ensemble are saying one thing and one saying the other thing. It's more likely to be the thing that they all kind of agreed upon. So that's just a very high level intuition behind it. And then we talked about last week Monte Carlo dropout. So Monte Carlo dropout involves keeping the dropout at test time. So the reason you do this is because when you think about how dropout works, because of its non-determinism, each time you apply a random dropout throughout the network, you have several sub-networks. So if you think about it, I might just draw it. So assuming that you have a dropout at test time when you're actually running, so on that would be one of your sub-networks. And then that might be another one. So that's why Monte Carlo dropout is referred to as an ensemble-like technique in this paper, because you can use it in the same way that by having one network, by applying dropout at test time, you kind of have a lot of sub-networks within that network. And it is the benefit to doing this would be in the context of deep neural networks, is that it's quite expensive to train an ensemble of deep neural networks, because each one of them will take a long time. So that Monte Carlo dropout was presented as a confidence-based prediction. So that's the thing we've been talking about before. Here's my prediction with this confidence, but it can actually be used, as shown in this paper, in the terms of a selection, in terms of a selective classifier where you can use the results to reject something. So, okay, and here is. So the main idea in this paper is to build a selective classifier, which is a pair of F and G. F is your standard classifier, so this would be your deep neural network, and G would be a rejection function. They'll be covered more formally, but just think about it as something that returns 1 or 0. So if G returns 1, it means the selective classifier is confident that it could classify the input. Otherwise, if it returns 0, it means it will abstain from voting. So it will say, I don't know, basically. And so the idea here is you want to classify, but with the highest coverage. So coverage is, so think about the extreme case, right? You can say, well, I don't want any training loss, so you just abstain from everything. So, and then your loss will be your classification error, which is basically 0. So you need to find a balance between the the risk of the model and the coverage. So you want to find there's a trade-off there. And now in this paper, so